Okay, so we're on to Module 6, Section 4, which is going to help us solve more exponential equations by introducing a new kind of function which is called the logarithm. Now, if you remember in the previous section, when we had an equation like 2 to the x equals 4, well, we tried to make these bases the same. So, for example, I can make this 2 to the x equal 2 squared, because 2 squared is 4, and then we just know x would equal 2. X is equal 2 is our solution, because 2 to the second equals 4. We also encounter some problems, such as 2 to the x equal 5, where there was not a good integer solution. So these logarithms are going to help us to solve this kind of problem, as well as have some other future applications. So a logarithm is related to the exponential function as they are inverse functions. So we actually can express these two functions in two different ways, one called exponential form and one called logarithmic form. And what they really are is they are just rearrangements of each other. So if I have an exponential, so y equal bx, and y can be anything. If I have y equal bx, then that can also be written as x equals the logarithm, we denote that log, base b of y. Now you'll notice all these things have the same things just in different places. The x that was in the exponent is now all by itself. The base of the logarithm b, the base of the exponential, is now the base of the logarithm. And then whatever was y by itself in the exponential now is inside the logarithm. So you actually can change these things to different forms by just putting them in different positions of this what we call logarithm. So the logarithm will always have a number down here which we call the base of some value. We'll call it, in this case, y. Okay? So this is a log base b of y is how we would read that. So these are inverse functions, so all those cool properties we knew before still will apply. So if we look at some different exponential statements that we know to be true, 2 to the second equals 4. Well, if I look at that relationship between the exponential and the log function, I can rewrite this a different way. I can say that this is the same as saying the log of base 2, because the base of the exponential is 2, whatever that value is 2 in our is the base in our logarithm, of 4, because whatever was by itself in the exponential goes inside the log, equals whatever the exponent was is 2. So log base 2 of 4 is equal to just 2. So if I were to able to put this in my calculator, which I eventually will, the log base 2 of 4 equals 2. Alright, same thing for the second one. We have 3 to the negative 4 equal 1/81st. So I can rewrite this as log. The log is base 3 of 1/81st. And again, the exponent in the exponential goes by itself in the logarithm. So the beauty of this is this exponent will now go by itself. This is particularly helpful when you think about things like equations that we can solve with exponential and log form. So if we have 4 to the x equals 16, if you notice that the x is in the variable, in the exponent, that's kind of a pain to get out of there. So if I switch it to log form, logarithm base 4, because the base of the exponential is 4, of 16 equals x. So by rearranging this, from changing it from exponential form to log form, what I do is I get the x by itself. I get whatever was in the exponent by itself, in this case, which is x. And then we can figure out what log base 4 of 16 is in a calculator. Or we should know that 4 to the second equals 16. So log base 4 of 16 actually is 2. But this is where this can be particularly helpful. If we have 2 to the x equals 7, we should know there's no way to get 2 from 7. But if I rewrite this in log form, this would be log base 2 of 7 equals x. So whatever this weird number, log base 2 of 7 is, and it's some irrational decimal number, whatever it is, that would be a solution to 2 to the x equals 7. So by switching from, again, exponential form to log form, makes these really helpful. The reverse is true as well. If we have stuff that are in log form, we can change them to exponential form. So these are in log form. My main clue that they're in log form is it says the word log. So if I reverse it, the base of the logarithm will be the same as the base of the exponential, so 7. But in this case, it's 7 to the third equals 343. So again, using this relationship from above, it tells you where everything goes. So in this case, we're in the log part, so we're going to take it in reverse. So the y will go by itself, so whatever was in the log, and the base goes there, and the variable goes, and the exponent goes there. So log base 7 of 343 equaling 3 can be the same as 7 to the third equals 343. Same thing here. If we look at this, this would be written as 5 to the negative fourth, base to that power, equals 1 over 625. When they have all numbers, they're really not helpful. It's just a little practice to show how the different forms do work out. So this last one, we have log base 4 of y equals 7. So I have a variable of y, but if I change it to exponential form, I get 4 to the 7th power, because I get the base of the log is the base of the exponential, exponent equals y. So y is just equal to 4 to the 7th, which is just 4 times 4 times 4 times 4, 7 times, whatever that might be. Well, now that we have the ways to get these into log form, it would be nice to be able to figure out what those values actually are in our calculator. And for this, we use what's called a change of base formula. The change of base formula is going to allow us to find the approximate value of a log expression. Now there are buttons on the calculator that definitely say the word log. So, but there's only, say, log. They don't have different bases for the log. It could be base 2, base 3, base whatever. So this change of base formula that helps us says if you have log base b of a, then this can just be written as 2 logs, log of a divided by log of b. And you can just type those in the calculator. You could type log parenthesis a divided by log parenthesis b. The key thing in the change of base formula is whatever is the base, the b, it has to go in the bottom of your quotient. So for example, if I want to know what log base 2 of 8 is, I can just type in log of 8 divided by log of 2. Again, the base goes on the bottom. Now I don't know what log of 8 divided by log of 2 is. But what I have here at the bottom is you can see I typed this into Desmos, and I just typed the word log parenthesis 8 divided by log parenthesis 2. So I just typed this expression in, and you will see this actually gives me what the value is. This is 3. So the log base 2 of 8 is 3. And I can check that. I do know that's true because if I change this log to exponential form, 2 to the third is 8. So that is correct. So Desmos, almost any graphing calculator, any scientific calculator can find these log expressions. Here's another one where we have the log base 7 of 24. So if I'm putting this in the calculator, I would simply put log of 24 divided by log of 7. Again, the only thing that'll mess you up is if you don't put the base on the bottom. And so see here, you see I have the log of 24 over the log of 7, and I get this weird decimal. 1.63319. So we'll say this is approximately 1.633. Now the question is this true? what is true. The calculator is not going to lie to us. But why do we know the log of 7 to the 24 is equal to about 1.633? Well, the reason is, if I check it, is 7 to the 1.633 equal to 24? So if you put 7 to the 1.633 in your calculator, you will find it gives you a value very, very close to 24. Okay, one more of the using the change of base. We have the log of base 3 of square root 18. So I can just write this as the log of the square root of 18, whatever is in the logarithm, divided by the log of 3. And I don't know what that is. It's not a nice number, but if you see here on Desmos, log of square root 18 over log of 3 will give us 1.315. So this is approximately 1.315 and more decimals. So the change of base gives us a really easy way to approximate what these log values are. Okay, so like I said, the main thing we'll be using this for is solving these exponential and log equations. So again, I will write the switching forms. So exponential, remember, y equals b to the x is the exact same as the log form of x equal log base b of y. So this will help us rearrange these when we're trying to solve them. So this first one says 16 to the x equals 64. So we're trying to figure out what this solution would be. So this is an exponential form, so I'm going to change it to log form. So the exponent, whatever it is, goes by itself. This would be log base 16, because 16 was our original base with our exponent, equals 64. So what is log base 16 of 64? Well, I could put that in my calculator as log of 64 over log of 16. And what this gives us is 1.5. So what we know, and you can check this, is 16 to the 1.5 equal to 64? You can check it, and it definitely is. So changing these exponentials, really a powerful tool in solving exponential equations. So let's look at the next one. We have 3 to the x equals 8. So this is an exponential form. Obviously, there's no log word. So we'll change it to log. So the exponent goes by itself, so x goes by itself, and that will equal log base 3, because that was the base of the exponent, of 8. So log base 3 of 8, so that can be written in the or typed in the calculator as log of 8 divided by log of 3. Whatever that is, these calculators have all these values stored. We used to use tables and charts, but now we use these calculators which can figure these values out really quickly. So the log of 8 divided by log of 3 is approximately 1.893. So what that tells us is 3 to the 1.893 should give us 8. It'll be close because, again, we have rounded it. All these values, all these decimals are rounded, but it'll give us something very close to 8. Well, this one's a little different because it has the plus 1 there, which is a little different. So I can still switch this to a log form. So I'll take the exponent, which in this case is an x plus 1. So x plus 1 equals log base 8 of 9. Again, the base goes to the base. So we have x plus 1, which was our exponent, and now I can figure out what log base 8 of 9 is by taking log of 9 divided by log of 8. Log of 9 divided by log of 8 is going to give me 1.057. So what I get is x plus 1 equals 1.057. So So now we don't have x by itself. We have this the 1, so I can simply subtract 1 from both sides to solve for x. So x equals 0.057. Okay, let's look at one more exponential equation, and then we'll look at a couple of log ones. So we have 3 times 2 to the x minus 2. Now this really isn't an exponential equation right now because you've got this random 3 out front. So we have to get rid of that first. So since it's multiplied to the exponential, I would simply just divide both sides by 3. That would make this 2 to the x minus 2 equals 8/3. And now I can turn it to log form. So I take the exponent, which in this case is x minus 2, that goes by itself, equals log base 2 of 8/3. So I don't know what log base 2 of 8/3 is, but if I type it in as log of 8 divided by 3 over log of 2, it will give me my approximate value. So log of 8/3 divided by log of 2 is going to give me 1.415. And then so to solve for x, I would simply just add 2 to both sides. So x is going to be 3.415. So we can also use this change of form things to solve things with logarithms. Like this has log values, log base 8n plus 1 equals 3. So if I change these to exponential, I can also solve these. So if I change this log to exponential, remember this base will now go by itself, and the exponent that was outside the log will now be the exponent of the exponential, equals n plus 1. So really all this stuff is a big rearrangement. That goes there, and then what's inside the log goes there. Base stays base. Whatever's by itself in the log becomes the exponent, just like whatever was the exponent goes by itself in the log. So 8 to the third, 8 times 8 times 8 is 512, equals n plus 1. And so I could simply subtract 1. So n equals 511. Okay, let's look at one more example. So we have log base 2 of x equals 7. So if I change this to exponential, I get 2, which was the base of the log, to the 7th, because that's what's by itself, would equal x. So in this case, the x goes by itself right away. So we're just left with 2 to the 7th. So 2 times 2 times 2 7 times is 128. Okay, so hopefully this introduction to log functions and solving exponential equations is okay. If you have questions, please let us know.